even though we spent a lot of time on the assignment and the warm-up. All right, figure ABCD is a rectangle with diagonals AC and BD. How can identifying corresponding parts of overlapping triangles help to prove that the triangles are congruent? Again, you had a problem just like this one on an assignment last week. It says consider triangle ABC and triangle DCB. So let's draw those separately. So ABC is this triangle right here. So here's A, here's B, here's C. And we have ourselves a right angle here, and we have a congruent length there. If we were to draw a triangle DCB separately, that would be this triangle right here. So here's B, here's C, and then D's up here. We got ourselves a right angle there, and then a congruent side there. And so what we're trying to do is show that the triangles are congruent and talk about congruent parts that correspond. So if we're talking about overlapping triangles, listen carefully here. Overlapping triangles include overlapping parts. The parts that overlap. Melina, facing this way. Thanks. Have a pencil? Yeah, writing it down. Did you draw these? Okay, do it then. All right. If there are two triangles that have overlapping parts, those overlapping parts could be side lengths, they could be angles, they could be parts of side lengths, they could be parts of angles. So do you notice any overlapping sides here? Yeah, BC and CB, they overlap. The bottom length of that rectangle is the bottom of each triangle, which means that those have to be congruent because it's the same side length on each triangle. Kind of like when two triangles don't overlap, but they back up to each other and they share a side. It's the same idea here. If they overlap full side to full side, then BC to CB is the same on both triangles because it's the bottom side of each triangle. So we would say that, and by the way, if we're looking at congruence here, BC, second and third letter here corresponds to CB, second and third letter there. So that the parts that correspond need to be written in the correct order. So from B to C on the first triangle is the same as from C to B on the second one. B to C, C to B. Right angle to bottom right corner, right angle here to bottom left corner. So B to C, C to B. All right, so we can say that BC is congruent to CB. I'm going to use the actual property here. It's the reflexive property. BC is congruent to CB by the reflexive property. Now, if we go and we actually look at the triangles here, we can say that triangle ABC is congruent to triangle DCB by what? What property can we use, or what theorem can we use to say that the triangles are congruent? Yeah, side angle side. We've got sides here, angle in between the two congruent sides, and another pair of congruent sides. So by SAS. There we go. So that's how we can use overlapping triangles. If you have a part that overlaps on both triangles, you can use that on both triangles. By the way, it says, let's see, how can identifying corresponding parts of overlapping to help prove? Okay, so good. All right, now, identifying corresponding parts. What are the corresponding sides and angles? So let's go ahead and just make a list here. So let's say sides, and then angles. Or if you wanted to use the symbol for angles, that's fine. Now, if you can see how these triangles overlap, great. If you have trouble identifying how things look when they are overlapped, draw them separately. So let's take a look. First one is triangle FHJ. By the way, it can also help if you want to. If you want to highlight them, you can do that. Yeah. So those are the two triangles right there that overlap. So if you can see how they overlap and you can see what parts correspond just by the way they look with their overlap, that's fine. Or maybe the easiest way to do it is what I suggested when we did our first lesson in this unit, and that is look at the congruency statements. That's probably the easiest way to figure it out. So we're talking about sides that are congruent here. One of the sides on triangle FHJ would be side length FH. So that means that FH corresponds to what on the other one? KH, yeah. And then from 2 to 3 be HJ corresponds to what? HJ corresponds to HG. And then FJ, first to third here, that's our third side. FJ corresponds to what? KG. So you don't actually need, and this is what I was going back to on that first day of notes for this unit, you don't actually need the diagram to visually see what parts correspond. If you have the congruency statement, you can just use the congruency statement. So for sides, that's it. Now, if you wanted to, if it didn't give you this congruency statement, something that you could do is you could go ahead and draw them separately. So like over here, we could go ahead and just draw these two triangles separate from one another, like that. And then H goes here, H goes here, F goes here, K goes here, J is here, and then G is there. Sorry, other way around. J is here, and G is here. And visually that way you can kind of see how things work with each other. We said FH was congruent to KH. So FH congruent to KH, that's that one right there. That's those two pairs. And visually you can kind of see how that works. HJ right here corresponds to HG right there. FJ, this one here, corresponds to KG, this one here. Now, in terms of angles, angle F corresponds to what? Is congruent to what? What's angle F congruent to on the other triangle? K, good. Angle F congruent to angle K. Angle H is congruent to angle what? Angle H, good. And then angle J congruent to angle G, good. So I'm just going to do 3 there, 3 here. We'll do 1 here, and then 2 there, and 2 there. So there we go. All the parts of both triangles shown to be congruent. If you have the congruency statement, I would suggest just using that to list it out. If you don't, and you have a hard time visualizing this together, draw them separately. That can be a help sometimes. All right. Any questions there before we continue? So far, it's just been a lot of visualization stuff, which actually is kind of the thing about overlapping triangles, is the visualization of it. So this next one is kind of interesting. Does anybody need more time here on this one right here? Nope. Okay, let's keep going then. Example 2. We are going to prove that triangle EGD is congruent to triangle EFH. Now, there's some hints here that kind of give us some ideas about what's going on. So the first thing that it mentions is that the large triangle, the overall triangle that encloses everything, DE is congruent to HE. And we learned in the first lesson of this unit that if you have a triangle that has 2 congruent side lengths, that means it's isosceles. And if you have an isosceles triangle, not only do you have 2 congruent sides, you also have 2 congruent angles, which means that angle D has to be congruent to angle H. So go ahead and measure that out, or show that they're congruent. The next thing it states is that since FG is congruent to FG, because it overlaps on both of them, We also have DF is congruent to HG. So this length here is congruent to that length there. That means that DG is congruent to HF. And I'll show you what that looks like in just a second. But it says it's congruent because of the segment addition postulate. That is not something we've used since Unit 2, a couple months ago. So I'm going to show you what they mean by that by drawing the two separate from one another. So we're drawing EGD and we're drawing EFH. So again, I'm going to go ahead and highlight these. So EGD is that one. EFH is this one. Those are the two triangles that we're dealing with that overlap. So if we draw these separately, I'm just going to draw as best as I can. That kind of looks almost equilateral, but whatever. There's D, there's E, there's G. And then the other one, look about like that. So there's F, there's H, and then here's E again. So if we draw them separately, they'll look about like that. Now, in terms of things that we know, from the original diagram, we know that DE is the same as EH. It tells us that. We also know that angle D has to be congruent to angle H because of the large isosceles triangle, making those two corners congruent to each other. So if we look at those two separate triangles, there's not enough information to say that we have right triangles, so we cannot use HL. So HL is out, which means we either have to use side, 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 which I would not recommend because we have a pair of angles. So get rid of side, side, side. So right here, the large triangle, DEH, the whole thing, because those two sides of that large triangle are congruent, it's isosceles, which means those two angles have to be congruent. Yeah. All right, so we've got that. We can't use side, well, I shouldn't say we can't. We shouldn't use side, side, side because we have a pair of angles. And we don't know about anything about right triangles, so that takes away two things. So that means we have side, angle, side, angle, angle, side, or angle, side, angle. So we either need to show one other pair of side lengths congruent, which is what we're going to do. It says right here. So let's just go ahead and talk about that for a second. So I want you to focus in on DG and HF. Those are the two other ones that we're going to show are congruent. Now, the only way that we can show that those two are congruent, D to G and H to F, and if you look here, it does not say that from D to G, as up here, please, does not say, thank you, does not say that from D to G is the same as from H to F. It doesn't give us that. It says that DF is the same as HG, which is not a side length on either one of those triangles. However, because the overlapping part, where the blue and the orange overlap here, see where that is right here? Blue and orange overlap here, FG, that overlapping portion has to be the same. So what it's saying is, just going to go ahead and do 3 little markings on FG here, because FG is the overlapping portion of those two triangles. So that means that DG, take a look, DG is a combination of a single mark and 3 marks. From D to G is a combination of single mark and 3 marks. Everybody see that? And from H to F is also a combination of a single mark and 3 marks. So you can put together 2 parts that are congruent as long as it's the same 2 parts that are congruent. You can use that to say that the larger segments are congruent. So that part and that part would be the same as this part and that part. Single, single, triple, triple. So those are congruent. And it's said by the segment addition postulate, right? Part of a segment plus another part of a segment equals a larger segment. And those 2 larger segments are congruent to each other. So what we can say is this. We can say DG is congruent to FH, like that. Or HF. And so because we have that, we're allowed to say that the triangles are congruent. So we're going to say triangle EGD is congruent to triangle EFH. And what are we using to prove that? Which theorem is proving that those are congruent? Yeah, SAS. Go back to the question. What is this problem telling us to prove? What does that say? Angles, yeah. We need to prove that a couple angles are congruent. So we're starting by saying that the triangles are congruent. We need to prove that EGD, this one here, is congruent to EFH, this one here. And we're allowed to do that now. CP, yeah, CP, CTC. Now that we've proved that the triangles are congruent, we're allowed to make statements about anything else. So we can now say that angle EGD is congruent to angle EFH by CPCTC. Nice. All right. Here's our next one. Are VW and ZY congruent? All right. Do we have overlapping triangles here? Down here at the bottom. Okay, what are the overlapping triangles? Okay, so let me draw that one here. So draw this as well, VWZ. So here's V, here's W, here's Z. What's the other one? CYV. Okay. Here's Z, here's Y, here's V. So if we're going to prove, here we go. If we're going to prove that VW and ZY, these two on the sides here, are congruent, what should we probably show first? That the triangles are congruent. All right, okay. Yeah. We could. It'll be more helpful for us in this situation. Well, actually, now that I look at it, we could use that. We could use all three triangles if we wanted to. That's fine too. There's a few ways to go through this. The only reason I'm showing this is because we're talking about overlapping, but that is an interesting thing here. We don't have to use the overlapping triangles to prove what we want to prove on this. And I'll show that in just a second too. You see it already, awesome. Let's keep working with this, but then I'll go back to here and show why we don't need to use the overlap. But can we say that this angle here, based on this right here, that part of angle V and that part of angle Z are congruent? We know that because it shows it to us. VZ has to be the same thing as ZV because they're congruent. That's the overlapping part, right? Everybody okay with that? The overlapping part has to be congruent. And then we can also say, take a look, this double and that single are the same as this double and that single. So we can say that that angle is congruent to that angle as well. And that's because of the angle addition postulate. So here we go. We're going to say that VZ is congruent to ZV by reflexive. We're going to say that angle WVZ is congruent to angle YZV by angle addition postulate because we're combining two angles. We're combining two angles from the original one to say that the two larger angles that they turn into are the same here. So that's the angle addition postulate. Now look at these two triangles. Do we have enough to say they're congruent? Yeah, by using what? Angle side angle. Okay, so we can say that triangle WVZ is congruent to triangle YZV by angle side angle. And that's enough to say that VW is congruent to ZY by CPCTC. So VW congruent to ZY by CPCTC. That is one way to solve this problem. That's using overlapping triangles. Now, Caitlin asked a good question. Can we use all three triangles that are in here? The answer is yeah, you can. Do you see a way to do that? Yes? How could we use all three triangles to show that those two sides are the same? Okay. You're talking about VX and ZX? Okay, I'm just gonna go ahead and mark this as congruent. You don't need to put this on your papers. Why do those have to be congruent? They are, but why do they have to? Anybody see it? Yeah. VXZ is an isosceles triangle. If those two angles are the same, those two sides have to be the same. So we are allowed to say that those two sides are the same because this middle triangle is isosceles. Now, something else we can do. Those are vertical angles. And now we can say that triangle WXV is congruent to triangle YXZ because of angle side angle on each one of those. So we don't actually have to use the overlapping triangles. We could use the two separate ones here plus this one as isosceles to say that those triangles are congruent, making that side congruent to that side by the same final reason, CPC. So there's a couple of ways you can reason your way through it. One of the nice things about geometry is that there's not always just one logical pathway to an answer. As long as you can back it up with factual information, there doesn't have to be only one way to solve something. So I think this is what the book was getting at because we're in an overlapping triangle section, but you don't have to use the overlapping triangles. So both would be valid. This question was on a test and you did either way there, you get full credit for either one because they both work. All right, last page, here we go. Got about 11 more minutes. By the way, tomorrow and Wednesday are going to be full on like review work days. So we might go to the end of class just to finish this up and then you'll have a lot of class time tomorrow and Wednesday to work. So a city runs 3 triangular bus routes to various attractions. How can you draw a separate triangle for each route? Are any of the routes the same length? So here we go. Here's our map. A lot of stuff going on there. All those decimal values, those are distances. So those are distances between stops is what that shows. So the green bus route stops. There we go. Green route. I know these didn't really print in green. So we're going Science Museum in green. We have the theater in green. We have the History Museum in green. We've got the Rose Garden in green. And we have the zoo in green. And then it goes back to the Science Museum. So there's the green route right there. That is a right triangle because of the corner right there at the Rose Garden. The next one is the purple route, which I also have that color. Great. So the purple route stops are at the water park right here. We also have the art museum, which is over here. We've got the concert hall, which is right there. The science museum, right there again. Up top. After the science museum, it goes to the zoo, which we've already seen before with the green one, and then it goes back to the water park. So here we have the purple route. Also a triangle. The final one is the red route. Should I use orange or pink for red?
Orange.
I heard pink first. Green, we already used green. All right. Red, imagine that's red. All right, football stadium. Start at the football stadium down here. So red, and then zoo. So all three of them stop at the zoo. Then the theater, which is up here. So green and red stop at the theater. Science Museum, all three stop at the Science Museum. Rose Garden, green and red at the Rose Garden, and then back down to the football stadium. So here is red route, which is shown by pink. Right there. All right. So here's our map. Got our colors. Use the map and the list of locations for each route to help you draw the triangles. Add length and angle information to your diagram. So here we go. Let's go with green first. So the green triangle looks like that. And it's a right triangle. We know that. This is the Rose Garden here. So I'm just going to say RG for Rose Garden. I'm going to say SM for Science Museum. And then what goes over here? HM for History Museum. Good. What is the total distance between the Science Museum and the History Museum? 3.5. Good. Because if you look here, 2.1, 1.4, add those together, 3.5. All right, how about the distance between the Science Museum and the Rose Garden? .1. 1.2 and 0.9. Yeah. And then the distance between the Rose Garden and the History Museum. It doesn't tell us, does it? Okay, let's leave that blank for a second then. Let's check out the purple route then. So here we go, purple route. So we've got the Science Museum here, we have the Art Museum down here, and then we have the water park down there. Distance between the Science Museum and the water park. Science Museum and water park, what's the distance? Was it 4.4? Good. So 4.4. How about the distance between the Art Museum and the water park? I think it's 3.1. No, wait. No, it's 2.9. You're right. It's 2.9. Because you got 0.9 here, 0.2 here, that's 1.1, 1.1 and 1.8 is 2.9. So 2.9. Good. 2.9 across the bottom. And then how about from the Art Museum back up to the Science Museum? 3.9. Good. Okay. And then the last triangle we have, this one is a right triangle because there is a right angle where the theater is right here. You can see that. So let's see, we're going to go there and then like that and then down like that. Okay, here's our right angle. The theater down to the football stadium and then up to the Science Museum. This is going to be, let's see, 2.1 goes here. The distance, let's see, 1.2, 0.9. We already did that distance already, didn't we? No, we didn't. We didn't do that distance yet. So 1.2, 0.9, 0.2, 0.3. 2.4 and 1.2 is, hang on. Did we miss a length somewhere? Which one? Oh, sorry, I should have decided it. Yeah, there we go. Okay. .1 and 1.1 is 3.2. 3.2 plus 3 is 0.3 is 3.5. Okay, there we go, 3.5. Okay. So there we go. Use the map, add length and angle information to draw the diagram. So the question here is, Are any of the routes the same length? Total routes. Are any of the total routes the same length? Like total triangular routes, are any of them equal? That looks like HL to me.
Oh.
Yeah? Certainly looks like HL to me. So we know that green and red are the same length. How can we show that they either are or are not the same length as purple? But in terms of the total length, the right angle shouldn't matter, right? Because we know the entire distance of purple because we can add all three of them together. How could we figure out the missing lengths here? Yeah, Pythagorean theorem. So we can use the Pythagorean theorem to figure out the distances here. Those two will be the same. And if we figure out the total distances, we already know that these two routes are the same, but maybe all three of them are the same. We don't know. But I'm going to stop you there for today because we only have 2 more minutes. So